The universe is accelerating away from itself. Every galaxy, every star, every photon of light rushing through the cosmic void is being pulled apart by something we cannot see, cannot touch, cannot explain. We call it dark energy. We say it makes up 70% of everything that exists. We build equations around it, write papers about it, stake entire careers on understanding it. But here's the truth that keeps cosmologists awake at night, staring at their data until dawn breaks over their laboratories. We have absolutely no idea what it is. None. Let that sink in for a moment. The dominant force in the universe, the thing that will ultimately determine the fate of every atom, every thought, every civilization that has ever existed or ever will exist, is a complete mystery. We've given it a name, packaged it into our models, taught it in universities across the world. But naming something doesn't mean we understand it. And understanding something, that doesn't mean it's real. What if dark energy is a lie? Not the kind of lie that someone tells you, but the kind the universe whispers to itself. A cosmic deception so fundamental that even our most sophisticated instruments can't see through it. What if everything we think we know about the accelerating expansion of space, about the ultimate fate of reality itself, is based on a misunderstanding so profound that future civilizations will look back at us the way we look back at those who believed the Earth was flat? You're probably thinking this sounds impossible. After all, we've measured the acceleration. We've tracked distant supernovae, mapped the cosmic microwave background, calculated the precise rate at which space itself is stretching. The evidence seems overwhelming, undeniable, carved into the very structure of space-time. But evidence can deceive. Mathematics can mislead. And sometimes, the most elegant explanation is just a beautiful mistake wearing the costume of truth. Consider this. In 1998, two teams of astronomers made a discovery that would shatter our understanding of cosmic destiny. They were studying Type Ia supernovae, stellar explosions so consistently bright that they could be used as cosmic measuring sticks, beacons scattered across billions of light-years that allowed us to map the expansion history of the universe. What they expected to find was deceleration, gravity's inevitable pull slowing down the outward rush of galaxies like a ball thrown into the sky, rising but gradually losing speed. What they found instead was acceleration. The universe wasn't slowing down, it was speeding up, and that should have been impossible. Imagine throwing a ball into the air and watching it accelerate upward, faster and faster, defying every law of physics you thought you understood. That's what the universe is doing. Every second that passes, the space between galaxy clusters grows at an ever-increasing rate. It's as if reality itself is running away from something, fleeing toward an unknown horizon at speeds that become more frantic with each passing eon. The scientists who made this discovery won the Nobel Prize. They had revolutionized cosmology overnight, transformed our understanding of the universe's past, present, and future. But they had also opened a door that perhaps should have remained closed. Because to explain this impossible acceleration, they had to invoke something even more impossible. A mysterious energy that permeates every cubic centimeter of space, pushing everything apart with a force that never diminishes, never weakens, never stops. They called it dark energy. Though dark doesn't really capture what it is. It's not dark like a shadow is dark. It's dark like the inside of a question that has no answer. Here's where things get disturbing. Dark energy doesn't just fill empty space. It is empty space. Or at least, that's one way to think about it. The vacuum of the cosmos, that perfect nothingness between stars, isn't actually nothing. It's seething with energy, bubbling with quantum fluctuations, alive in ways that defy our intuition about what emptiness should be. And this energy has a property unlike anything else in physics. It has negative pressure. While matter and radiation pull things together through gravity, dark energy pushes them apart through anti-gravity. It's as if the universe is filled with invisible springs, all compressed and pushing outward. And no matter how much the universe expands, these springs never lose their tension. But why? Why would empty space have energy? Why would this energy create a repulsive force? And why? This is the question that should haunt you. Why is the amount of dark energy so perfectly balanced that the universe is neither collapsing nor expanding too quickly to form structures, like galaxies and stars and planets and you? The value of dark energy seems fine-tuned, calibrated with impossible precision to allow for the existence of complexity. Change it by even a minuscule fraction, and the universe becomes a sterile wasteland where nothing interesting can ever happen. This is called the cosmological constant problem, and it's arguably the deepest crisis in modern physics. When you try to calculate how much dark energy should exist based on quantum field theory, you get a number that's wrong by a factor of 10 to the power of 120. That's not just wrong. That's laughably, absurdly, inconceivably wrong. It's like predicting someone weighs 200 pounds and then discovering they actually weigh less than a single atom. Across the entire observable universe, the mathematics of reality seems to be screaming at us that dark energy shouldn't work the way it does, or perhaps that it shouldn't exist at all. So what if it doesn't? What if dark energy is our generation's version of epicycles, those elaborate mathematical constructions that ancient astronomers used to explain planetary motion before we realized the Earth wasn't the center of everything? For centuries, the epicycle model worked. It made predictions, matched observations, satisfied the equations. It was also completely wrong. The underlying assumption that Earth was stationary and everything revolved around it was false, and no amount of mathematical sophistication could make it true. Could we be making the same mistake? Are we adding dark energy to our equations because our fundamental assumptions about the universe are wrong? Maybe space doesn't expand the way we think it does. Maybe our understanding of gravity breaks down at cosmic scales. Maybe time itself flows differently across vast distances, creating illusions of acceleration where none truly exists. Maybe the light from distant supernovae has been altered in ways we haven't imagined by its billion-year journey through the cosmos. Maybe, just maybe, we're interpreting the data correctly, but misunderstanding what it means. You might be wondering, if dark energy is a mistake, wouldn't scientists have figured that out by now? After all, cosmology is one of the most rigorous sciences we have. Every measurement is checked and rechecked, every theory tested against multiple lines of evidence. The discovery of cosmic acceleration wasn't accepted immediately. It was scrutinized, challenged, verified through countless independent observations. Dark energy isn't some fringe idea. It's the foundation of our current cosmological model, supported by data from supernovae, from the cosmic microwave background, from the large-scale structure of galaxies. from gravitational lensing studies. How could all of this be wrong? But here's the uncomfortable truth. Science has been spectacularly wrong before, even when the evidence seemed overwhelming. For decades, we believed in a static universe because that's what made sense, what felt right, what matched our philosophical assumptions about eternity and permanence. Even Einstein added his cosmological constant, the very thing that would later become dark energy, not to explain acceleration, but to keep the universe frozen in time, unchanging, eternal. When Hubble discovered that galaxies were rushing away from us, that the universe was expanding, Einstein called his cosmological constant his biggest blunder. He removed it from his equations, admitting he had forced the mathematics to match his expectations rather than letting reality speak for itself. Now, decades later, we've put the cosmological constant back. We've resurrected Einstein's blunder and declared it the solution to our problems. But what if we're making the same mistake he did? What if we're forcing our equations to match our observations without understanding that both the equations and the observations might be telling us something completely different from what we think? Let's go deeper. Let's question everything. When you look up at the night sky, you're not seeing the universe as it is. You're seeing the universe as it was. The light from distant stars and galaxies has been traveling for years, centuries, millennia, billions of years before reaching your eyes. You're looking backward through time, watching ancient history play out in real time. The most distant objects we can observe are so far away that their light has been traveling since the universe was young, when the first stars were just beginning to ignite in the primordial darkness. And here's the thing. Those distant objects are moving away from us faster than nearby ones. The farther away something is, the faster it recedes, as if the universe is expanding uniformly in all directions. This is Hubble's law, the cornerstone of modern cosmology, confirmed through countless observations. But space itself is expanding. It's not that galaxies are moving through space away from us. It's that the space between us and them is growing, stretching, inflating like a balloon being filled with air. And if space can expand, then it can also accelerate, which is exactly what we observe. Or is it? Because when you look at those distant supernovae, those cosmic lighthouses that revealed the acceleration, you're making some profound assumptions. You're assuming that the supernovae we see billions of light-years away are identical to the supernovae we observe in nearby galaxies. You're assuming that the light traveling across the cosmos hasn't been affected by anything strange or unexpected during its journey. You're assuming that our understanding of how light redshifts, how its wavelength stretches as space expands, is correct. You're assuming that nothing about the early universe was fundamentally different from today. What if any of these assumptions is wrong? What if supernovae in the early universe were subtly different from nearby ones in ways we can't detect? What if intergalactic space isn't truly empty, but filled with tenuous clouds of exotic matter that dim distant light in unexpected ways? What if our galaxy sits in a local void, a region where matter density is lower than average, creating the illusion of acceleration when really we're just seeing the effect of inhabiting an unusual cosmic neighborhood? What if the laws of physics themselves evolve over cosmic time scales, slowly changing in ways so subtle that we can't measure them except through their effects on the most ancient light? These aren't just idle speculations. These are serious alternatives that physicists have proposed, investigated, and, in some cases, found difficult to rule out completely. The universe is vast and strange, and our ability to probe its secrets is limited by the speed of light, by the resolving power of our telescopes, by the finite sensitivity of our instruments. We're like ancient explorers who have sailed to the edge of the known world and reported back that there are monsters in the deep. Except we can't bring back a specimen, can't confirm that what we saw wasn't a trick of the light, can't be absolutely certain that we're interpreting the distant shadows correctly. And there's something else, something even more unsettling. The amount of dark energy seems to be constant, the same in every cubic meter of space, unchanging throughout time. As the universe expands and matter becomes more diluted, spread thinner across ever greater volumes, dark energy maintains its density. More space means more dark energy, as if empty space is inherently creative, continuously generating this mysterious force out of nothing. This violates our intuition about conservation laws, about the impossibility of creating something from nothing. Where does this energy come from? How can space produce infinite energy without drawing it from anywhere? The standard answer involves quantum field theory and vacuum energy, and the Heisenberg uncertainty principle. Concepts so abstract that even physicists sometimes admit they're working with mathematical convenience rather than genuine understanding. We say that empty space isn't truly empty, that it's filled with virtual particles constantly popping in and out of existence, borrowing energy from the universe on credit that they repay instantly before anyone, even the cosmos itself, notices. And somehow, the collective effect of these quantum fluctuations creates a background energy density that pushes space apart. But when you calculate how much energy these fluctuations should produce, you get that catastrophically wrong answer, 10 to the power of 120 times too much. It's as if the mathematics is telling us we're asking the wrong question, using the wrong concepts, missing something so fundamental that all our sophisticated equations become meaningless. Imagine trying to predict the weather using a map of ancient Rome. The map might be detailed, accurate, beautifully drawn, and completely useless for the task at hand because you're applying it to the wrong context. Could dark energy be the wrong context? Could we be mapping our mathematical models onto a reality that doesn't match our assumptions? The universe has surprised us before. When quantum mechanics was first developed, it revealed that particles could be waves, that observation affects reality, that uncertainty is built into the fabric of existence. When general relativity emerged, it showed us that space and time are malleable, that gravity is geometry, that black holes, once thought to be mathematical curiosities, are real objects that devour everything, even light itself. Each revolution in physics has revealed that our previous understanding was incomplete. That reality is stranger and more subtle than our theories suggested. What if we're on the cusp of another revolution? One that will make dark energy seem as quaint and misguided as the luminiferous ether, that invisible substance 19th-century physicists believed filled all of space and carried light waves. They had good reasons to believe in the ether, strong theoretical reasons supported by the best physics of their time. They were also completely wrong. The ether doesn't exist. It never did. And when Einstein showed that light doesn't need a medium to propagate through, that space and time are relative rather than absolute, The entire theoretical framework collapsed overnight. Could dark energy be our ether? Our elaborate explanation for something that will eventually be explained more simply, more elegantly, by a deeper understanding of how reality works. There are physicists who think so. They propose alternative theories of gravity that don't require dark energy, modifications to general relativity that become significant at cosmic scales, new symmetries and fields and dimensions that change how we think about the expansion of space. None of these alternatives have gained universal acceptance. But that doesn't mean they're wrong. It might mean we're not ready to accept what they imply about the universe. Because here's the really uncomfortable possibility. What if there is no dark energy, and the universe isn't accelerating at all? What if we're misinterpreting the data, seeing patterns that aren't there, constructing elaborate theories to explain observations that have simpler explanations we haven't thought of yet? What if the redshift of distant supernovae is telling us something about the nature of light, or about the evolution of cosmic structures, or about variations in the expansion rate across different directions in space, rather than about a mysterious force pushing everything apart? This would be devastating to modern cosmology. We've built entire edifices of theory on the foundation of dark energy. We've predicted the ultimate fate of the universe based on it. A cold, dark, lonely future where galaxies drift apart, where the cosmic background radiation cools to near absolute zero, where the last stars eventually burn out and leave behind a universe of black holes slowly evaporating into nothing through Hawking radiation over timescales so vast they make the current age of the universe seem like a single heartbeat. We call this the Big Freeze, the heat death, the ultimate triumph of entropy over order. And it all depends on dark energy continuing to dominate and accelerate the expansion forever. But what if this prediction is wrong? What if the universe has a different fate waiting? One we can't imagine because we're working from flawed assumptions. What if the acceleration we observe is temporary, a phase that will end when some unknown condition is met? What if space has limits we haven't discovered, boundaries or cycles or strange topologies that change everything about how expansion works? What if we're living through a unique cosmic epoch, one that future or past civilizations wouldn't recognize, where the laws of physics manifest in unusual ways? You see, this is the terrifying beauty of cosmology. We get exactly one universe to study, one sample size, one cosmic experiment that we can never repeat or control. We can't create universes in laboratories to test our theories. We can't rewind time and watch the Big Bang happen again with different initial conditions. We're forced to infer everything from the light that reaches us, from the faint whispers of radiation left over from the universe's infancy, from mathematical models that might be elegant but could be entirely divorced from reality. And yet we speak with such confidence. We claim to know that the universe is 13.8 billion years old, that it contains billions of galaxies, each with billions of stars, that it's flat in its geometry, that it began with a singularity and will end in darkness. We've mapped the cosmic microwave background with exquisite precision, detected gravitational waves from colliding black holes, found planets orbiting distant stars. Our cosmological model, the Lambda CDM model, named for the cosmological constant lambda that represents dark energy, fits the data beautifully, almost too beautifully. Because sometimes, when a theory fits too well, when it explains everything just a bit too neatly, that's a warning sign. Nature is messy, chaotic, full of exceptions and anomalies and surprises. When our models become too clean, too perfect, too self-contained, we should wonder if we're describing reality or just describing our own biases and expectations reflected back at us. Are we discovering the universe, or are we inventing it? Think about what dark energy implies. It suggests that most of the universe, 70% of all energy, the dominant component of reality, is something we've never detected directly, something that only reveals itself through its gravitational effects on the largest scales imaginable. We can't capture it in a bottle, can't study it in isolation, can't even say with certainty what it's made of, or whether it's made of anything at all. We've essentially said, there's this invisible, undetectable thing that fills all of space and determines cosmic destiny. And you should trust us that it exists because our equations require it. Doesn't that sound just a little bit like faith? Not religious faith, necessarily, but a kind of theoretical faith that our mathematical frameworks are correctly describing reality even when we can't verify their most important predictions? We've accepted dark energy into our cosmological doctrine because the alternative is too disturbing, admitting that we might be fundamentally confused about how the universe works. And maybe we should be more disturbed. Maybe we should lose sleep over the fact that dark energy appears in our equations almost as an afterthought, a constant term added to make the math work out, with no deeper physical insight into why it should have the value it does, or why it should exist at all. Einstein introduced the cosmological constant to keep the universe static, then removed it when that turned out to be wrong. We've reintroduced it to make the universe accelerate. But are we making the same kind of mistake? Forcing nature to fit our theories instead of letting nature reveal its true character? Consider the arrogance embedded in our cosmological narrative. We've decided that the universe had a beginning, the Big Bang, based on the observation that everything is moving apart, which suggests that if you run time backward, everything converges to a point. But what if space and time don't work that way at the extremes? What if the universe is cyclic, bouncing through infinite expansions and contractions? What if our Big Bang was just a local event, a bubble forming in an eternal multiverse? What if time doesn't have a beginning at all, and the very concept of asking what came before is meaningless because time itself is an emergent property that only makes sense within certain contexts? These are not idle philosophical musings. These are legitimate scientific questions that challenge the foundations of our cosmological thinking. And dark energy sits at the heart of this challenge because it represents the ultimate cosmic unknown. The thing we claim explains everything while explaining nothing. The placeholder we've inserted into our theories until we figure out what's really going on. So let's ask the forbidden question, the one that makes cosmologists uncomfortable. What if we're completely, utterly, spectacularly wrong about all of this? What if dark energy is the Emperor's new clothes, a collective hallucination dressed up in mathematical formalism? What if a century from now, students will learn about dark energy the way we learn about phlogiston and the four humors and spontaneous generation, as examples of how even brilliant scientists can convince themselves of nonsense when the evidence is ambiguous and the need for explanation is desperate? The universe is accelerating away from itself. This is what we observe. But observation is not understanding. Correlation is not causation. And sometimes the data whispers lies that sound like truth. To understand why dark energy represents such a profound mystery, You need to understand what we thought we knew about the universe before 1998 shattered everything. You need to travel back to a time when cosmology seemed settled, when the questions had been answered, when the fate of the cosmos appeared inevitable and predictable. Because that certainty, that beautiful, comfortable certainty, was an illusion. And recognizing that illusion is the first step toward seeing how deeply we might be deceived about dark energy itself. The story begins almost a century ago, in a time when the universe was thought to be much smaller than we now imagine. Back then, the Milky Way wasn't just our galaxy. It was the galaxy, the entirety of existence, an island of stars surrounded by infinite empty darkness. Astronomers had observed fuzzy patches of light called nebulae scattered across the sky. But most believed these were merely clouds of gas within our own galactic neighborhood, stellar nurseries where new stars were being born, or the remnants of old stars that had died violent deaths. Then came Edwin Hubble, working at the Mount Wilson Observatory in California, peering through what was then the world's largest telescope at a nebula in the constellation Andromeda. What he discovered changed everything. The fuzzy patch wasn't a gas cloud at all. It was another galaxy, a vast collection of hundreds of billions of stars, so distant that its light had been traveling for millions of years before reaching Earth. And if Andromeda was a separate galaxy, then perhaps all those other nebulae were galaxies too, each one a universe unto itself, scattered through space like islands in an ocean far vaster than anyone had imagined. But Hubble's most important discovery came when he measured how fast these galaxies were moving. He found that almost every galaxy was rushing away from us, fleeing into the cosmic darkness at tremendous speeds. And here's what made this discovery revolutionary. The farther away a galaxy was, the faster it was receding. Double the distance, double the velocity. Triple the distance, triple the speed. This wasn't random motion. It was a pattern, a cosmic law that revealed something fundamental about the nature of space itself. Hubble had discovered that the universe is expanding, not expanding into anything, not spreading out through some pre-existing void, but expanding in a way that's almost impossible to visualize because it involves the creation of space itself. Imagine you're standing on the surface of a balloon, and someone is inflating it. You're not moving across the balloon's surface, but the surface itself is stretching, carrying you along with it. Every point on the balloon is moving away from every other point. Not because anything is traveling through space, but because space itself is growing. This is what's happening to the universe. Space is stretching, and as it stretches, it carries galaxies along with it like raisins in rising bread dough. The galaxies themselves aren't moving through space. They're being carried by the expansion of space itself. And the farther apart two galaxies are, the more space exists between them to expand, which is why more distant galaxies recede faster. It's not that they're moving faster through space, it's that there's more space between us and them to do the expanding. Now, if the universe is expanding today, that means it was smaller in the past. Wind the clock backward and everything gets closer together. The galaxies converge, the space between them shrinks, the universe becomes denser and hotter. Keep rewinding, and eventually you reach a point where all the matter and energy in existence is compressed into an unimaginably tiny, unimaginably hot, unimaginably dense state. This is the Big Bang. Not an explosion that happened somewhere in space, but an explosion of space itself. The moment when the universe burst into existence and began its outward rush that continues to this day. Or so we've been told. Because here's where the first crack appears in this cosmic narrative. The Big Bang isn't something we observed. We've never seen it happen. We've never traveled back in time to confirm that the universe actually began this way. What we have are observations of the universe today and mathematical models that, when run backward, suggest there was a beginning approximately 13.8 billion years ago. But those models depend on assumptions. Assumptions about how gravity works, about the nature of space and time, about the laws of physics remaining constant throughout cosmic history. What if those assumptions are wrong? What if the universe doesn't have a beginning? What if time stretches infinitely into the past, and what we call the Big Bang was merely a transition, a phase change, one moment in an eternal cosmic cycle? What if space and time behave so strangely at extreme densities that our equations break down completely, becoming meaningless, and the entire concept of a singular beginning is just our mathematical models hitting a wall they can't penetrate? But let's set aside these doubts for the moment and accept the standard story. Let's say the universe did begin with the Big Bang, approximately 13.8 billion years ago. In that first instant, space itself erupted from nothing, or from some quantum fluctuation, or from a previous universe's collapse, or from causes we can't fathom, and began expanding at an extraordinary rate. The early universe wasn't just hot, it was a furnace where time itself was still learning to move, where the familiar forces of nature were merged into a single unified force, where particles and antiparticles flickered in and out of existence so rapidly that the concepts of particle and energy were almost meaningless distinctions during the first fraction of a second, an impossibly brief instant that makes a single heartbeat seem like an eternity. The universe underwent a period called cosmic inflation. This is one of the strangest ideas in all of cosmology, and it's worth dwelling on because it sets the stage for understanding why dark energy is so perplexing. According to inflation theory, the newborn universe expanded exponentially, doubling in size over and over again, growing from smaller than an atom to larger than a galaxy in less time than it takes light to cross the nucleus of an atom. In that brief instant, space expanded faster than the speed of light. Wait, faster than light? Didn't Einstein prove that nothing can travel faster than light? He did, and that's still true. But here's the trick. Nothing can travel through space faster than light, but space itself isn't constrained by that speed limit. Space can expand at any rate it wants, carrying matter and energy along with it, without violating relativity. Galaxies at the edge of the observable universe are receding from us faster than light right now, not because they're moving through space at superluminal speeds, but because the space between us and them is expanding so rapidly that light cannot keep up. Inflation solved several deep puzzles about the universe. It explained why space is so flat, why the cosmic microwave background radiation has almost the same temperature in every direction, why we don't see magnetic monopoles and other exotic relics that should have been produced in the Big Bang. It took problems that seemed unsolvable and made them disappear through a single elegant mechanism: exponential expansion in the first moment of cosmic history. But inflation also created new mysteries. What caused it? What turned it on and what turned it off? If inflation could happen once, why doesn't it happen again? And here's the question that should haunt you. If space can expand exponentially during inflation, driven by some mysterious energy field that filled the early universe, could space be expanding exponentially now, driven by a different mysterious energy field that fills the current universe? Could dark energy be inflation's distant cousin, a related phenomenon operating in a different cosmic era? After inflation ended, the universe continued to expand, but now at a slower, more sedate pace. As space grew, the incredible heat of the Big Bang cooled, like a furnace with its doors thrown open to the cosmic void. Energy condensed into particles, first quarks and electrons, then protons and neutrons, eventually atoms of hydrogen and helium, the primordial elements from which everything else would be built. For hundreds of thousands of years, the universe was opaque, filled with a hot fog of matter and radiation so dense that light couldn't travel more than a short distance before being scattered. You couldn't have seen your hand in front of your face if you'd existed then, because photons couldn't make the journey from your hand to your eyes without being absorbed and re-emitted countless times. Then came a moment cosmologists call recombination, when the universe had cooled enough for electrons to settle into stable orbits around atomic nuclei. Suddenly, space became transparent. Light could travel freely for the first time, racing through the cosmos unimpeded. The photons released at that moment, the first light to travel through a transparent universe, are still traveling today, stretched and cooled by billions of years of cosmic expansion into microwave radiation that fills all of space. This is the cosmic microwave background, the afterglow of the Big Bang, a baby picture of the universe when it was only 380,000 years old. When we study this ancient light, we see patterns, tiny temperature variations, slight differences in density from one region to another. These variations are the seeds that would eventually grow into galaxies and clusters and the vast cosmic web of structure we see today. Gravity amplified these small differences over billions of years, pulling matter together into clumps, forming the first stars when the universe was only 100 million years old, assembling those stars into galaxies, gathering galaxies into clusters, weaving everything into an intricate tapestry of cosmic structure. This is the universe as we understand it, born in fire, expanding and cooling, organizing itself through gravity into structures of ever-increasing complexity, giving rise eventually to stars that forge heavy elements in their cores, to planets that orbit those stars, to chemistry and biology and consciousness, to beings who can look up at the night sky and wonder where it all came from. It's a beautiful story, scientifically rigorous, supported by mountains of evidence. And for decades after Hubble's discovery, the central question in cosmology was deceptively simple. How fast is the expansion slowing down? Because gravity should slow it down. That was the certainty, the unquestioned assumption that shaped decades of astronomical research. The universe is full of matter. Stars and planets and gas clouds and dark matter, all of it exerting gravitational attraction, all of it pulling on everything else. Gravity can't accelerate expansion. It can only decelerate it, acting as a cosmic brake on the outward rush of galaxies. The only question was whether gravity was strong enough to eventually halt the expansion and reverse it, causing the universe to collapse back on itself in a big crunch that would mirror the Big Bang, or whether the expansion would continue forever, gradually slowing but never quite stopping. carrying galaxies away from each other into an ever colder, ever darker future. Astronomers set out to measure this deceleration, to determine the ultimate fate of the universe by studying how the expansion rate has changed over cosmic history. And this is where supernovae enter the story. Not just any supernovae, but a specific type called Type Ia. Stellar explosions so reliable that they could be used as cosmic mile markers, beacons that allow us to measure distances across billions of light years. Type Ia supernovae occur when a white dwarf star, the dense, collapsed core left behind when a star like the Sun exhausts its fuel, accumulates too much mass from a companion star. White dwarfs are supported by quantum mechanical pressure, the refusal of electrons to be compressed beyond a certain limit. But there's a maximum mass a white dwarf can have before even this quantum pressure can't hold it up anymore. That mass is precisely 1.4 solar masses, a limit discovered by Subrahmanyan Chandrasekhar, and now called the Chandrasekhar limit in his honor. When a white dwarf crosses this threshold, it collapses catastrophically. The sudden compression ignites a runaway nuclear fusion reaction that tears the star apart in an explosion so bright it can briefly outshine an entire galaxy. And here's the crucial part. Because every Type Ia supernova is caused by a white dwarf crossing the same mass limit, every Type Ia supernova should release approximately the same amount of energy and reach approximately the same peak brightness. They're like light bulbs with a standard wattage, cosmic calibration sources scattered throughout the universe. If you observe a Type Ia supernova and it appears dim, that's because it's far away. If it appears bright, it's relatively nearby. By measuring the apparent brightness and comparing it to the absolute brightness these explosions should have, you can calculate the distance. And by measuring the redshift of the light, how much its wavelength has been stretched by cosmic expansion, you can determine how fast space was expanding when that light was emitted. Plot distance against redshift for many supernovae at many different distances, and you can map out the expansion history of the universe, watching how the expansion rate has changed over billions of years. This was the project undertaken by two competing teams in the 1990s, the Supernova Cosmology Project led by Saul Perlmutter, and the High-Z Supernova Search Team led by Brian Schmidt and Adam Riss. Both teams were hunting for distant supernovae. Both were meticulously measuring their brightness and redshift. Both were expecting to find evidence of deceleration. The only question was how much deceleration. Would the universe eventually recollapse? Or would it expand forever while gradually slowing down? Neither team expected what they actually found. The distant supernovae were dimmer than they should be. Not a little dimmer, significantly dimmer, as if they were farther away than predicted by a decelerating expansion model. And the only way to make the data fit was to conclude that the expansion of the universe wasn't slowing down at all. It was speeding up. Distant galaxies were moving away faster than they should be if gravity were the only force at work. Something was pushing them, accelerating them, driving space to expand at an increasing rate. At first, the scientists couldn't believe it. They checked their data obsessively, looking for errors, systematic biases, anything that might explain away this impossible result. They worried that dust between galaxies might be dimming the light, making distant supernovae appear farther away than they really were. They wondered if supernovae in the early universe might be intrinsically different from modern ones, evolving over cosmic time in ways that would mimic acceleration. They considered whether gravitational lensing, the bending of light by matter, might be distorting their measurements. But the effect persisted. No matter how they analyzed the data, the conclusion remained: the universe is accelerating. And in 1998, both teams announced their findings almost simultaneously, unleashing a revolution in cosmology that continues to this day. The discovery was so unexpected, so paradigm-shattering, that it took years for the scientific community to fully accept it. But as more data accumulated, as new observations confirmed the acceleration through independent methods, the reality became undeniable. The universe is indeed speeding up, and something must be causing this acceleration. That something is what we call dark energy. But naming it doesn't explain it. We've simply attached a label to our ignorance, given a title to the unknown. What is dark energy? Where does it come from? Why does it exist? How does it work? These questions remain unanswered, hidden behind a wall of mathematical formalism that describes the phenomenon without truly illuminating it. Here's what we think we know, or what we've convinced ourselves we know. Dark energy appears to be a property of space itself, an energy that pervades every cubic centimeter of the cosmos. Unlike matter, which clumps together into galaxies and stars, dark energy is perfectly uniform, the same everywhere, unchanging in density even as space expands. Imagine a substance where adding more volume doesn't dilute it, where creating more space automatically creates more of this mysterious energy, as if emptiness itself has weight and pressure and the power to shape cosmic destiny. And this energy has a bizarre property: negative pressure. In normal physics, pressure pushes outward. The air in a balloon pushes against the rubber, trying to expand. But negative pressure pulls inward, creating tension rather than compression. Except in general relativity, negative pressure has a counterintuitive effect on gravity. It creates repulsion rather than attraction, anti-gravity rather than normal gravity. Dark energy's negative pressure overwhelms its positive energy density, and the net effect is a repulsive gravitational force that pushes space apart. This makes dark energy the opposite of matter. Matter attracts. Dark energy repels. Matter slows the expansion. Dark energy accelerates it. Matter clumps. Dark energy spreads uniformly. Matter's density decreases as the universe expands, like spreading a fixed amount of butter over ever larger toast. But dark energy's density remains constant, as if the universe is continuously creating new butter out of nothing to maintain the same thickness no matter how much the toast grows. How can energy be created from nothing? Doesn't that violate conservation of energy? One of the most sacred principles in physics? Actually, no, or at least, not in the way you might think. In an expanding universe, energy conservation becomes subtle and strange. The expansion of space itself can do work, can create or destroy energy in ways that seem impossible in everyday physics. When space expands, photons lose energy. Their wavelengths stretch. Their frequencies decrease, and that lost energy simply disappears into the expansion itself. Similarly, dark energy can gain energy as space grows, drawing it from the expansion process in a cosmic shell game where energy appears to be created, while the total accounting somehow remains balanced. This is deeply weird. It's counterintuitive enough that even physicists sometimes struggle to explain it, without resorting to equations and mathematical abstractions. But the weirdness doesn't stop there. Remember that catastrophically wrong prediction from quantum field theory? The calculation that says vacuum energy should be 10 to the power of 120 times larger than what we observe? Let's dwell on that for a moment, because it reveals just how confused we are about dark energy. Quantum field theory is one of the most successful theories in all of physics. It combines quantum mechanics with special relativity to describe how particles and forces work at the smallest scales. It's been tested to extraordinary precision. Some of its predictions match experiments to 1 part in a trillion. It's the foundation of the Standard Model of particle physics, the theory that describes every particle and force except gravity. When quantum field theory makes a prediction, we trust it. When it tells us something should happen, that thing usually happens, often with stunning accuracy. But when you ask quantum field theory how much energy empty space should have, it gives you an answer that's wrong by a factor so large that it defies comprehension. To put this in perspective, if you predicted someone weighed 200 pounds, and they actually weighed the mass of a single electron, you would be wrong by a factor of about 10 to the power of 30. Quantum field theory's prediction for vacuum energy is wrong by 10 to the power of 120. That's a 1 followed by 120 zeros. It's not just wrong, it's absurdly, incomprehensibly, almost insultingly wrong. This is the cosmological constant problem, and it's arguably the deepest crisis in theoretical physics. It suggests that our understanding of quantum mechanics, or our understanding of gravity, or our understanding of the relationship between them is profoundly flawed. It's as if nature is telling us we're asking the wrong question, using the wrong concepts, misunderstanding something so fundamental that all our sophisticated mathematics becomes meaningless noise. Some physicists suggest that perhaps virtual particles, those quantum fluctuations that pop in and out of existence in empty space, don't actually contribute to the vacuum energy in the way we think they do. Maybe there's a cancellation mechanism we haven't discovered, some symmetry or principle that forces the vacuum energy to be much smaller than naive calculations suggest. But if such a mechanism exists, we haven't found it. And any cancellation would have to be tuned to extraordinary precision, balancing positive and negative contributions to 120 decimal places. That kind of fine-tuning seems implausible, almost miraculous, suggesting either that we're incredibly lucky or that we're missing something profound about how the universe works. Other physicists propose that maybe the vacuum energy is actually as large as quantum field theory predicts, but it somehow doesn't gravitate, doesn't affect the expansion of space. But that requires inventing new physics, new principles that separate energy's role in quantum mechanics from its role in general relativity. It means abandoning one of the foundational ideas in physics, that energy and mass are equivalent, that anything with energy contributes to gravity. And abandoning that principle would require rebuilding much of modern physics from the ground up. Still others suggest we're simply wrong about dark energy being vacuum energy. Maybe it's something else entirely. A new field that fills space, perhaps slowly evolving over time, perhaps interacting with matter or radiation in subtle ways we haven't detected. Physicists call this hypothetical field quintessence, named after the ancient Greek fifth element that was supposed to fill the heavens. But calling it quintessence doesn't make it any less mysterious. We still don't know what it is, where it came from, or why it has exactly the right properties to explain the observed acceleration. And then there are the radicals who suggest that maybe dark energy doesn't exist at all, that we're interpreting the data incorrectly because our underlying theory of gravity is wrong. Einstein's general relativity has passed every test we've thrown at it for over a century. But all those tests have been conducted on relatively small scales, within our solar system, around binary pulsars, near stellar mass black holes. We've never really tested general relativity on cosmological scales across billions of light-years in the ultra-weak gravitational fields that dominate the space between galaxy clusters. Maybe gravity works differently on these vast scales. Maybe the equations need modification, additional terms, new symmetries that only become important when you're dealing with the universe as a whole. Modified gravity theories are controversial, often dismissed by mainstream cosmologists as desperate attempts to avoid accepting dark energy. But they deserve consideration, because they address a legitimate question. How confident can we be that Einstein's equations, derived and tested in one context, apply perfectly in a completely different context? We're extrapolating from small-scale experiments to the entire observable universe, from strong gravitational fields to the weakest fields imaginable, from laboratory timescales to billions of years. That's an enormous extrapolation, and history teaches us that physical theories often break down when pushed far beyond their original domain. Consider this. Newton's law of gravity worked perfectly for centuries. It explained planetary orbits, predicted the existence of Neptune, seemed like an eternal truth about the universe. But it was wrong. It was an approximation that worked beautifully in weak gravitational fields and at low velocities, but failed completely near black holes and at speeds approaching light. Einstein didn't just modify Newton's theory, he replaced it with a completely different framework, where gravity isn't even a force, it's the curvature of space-time itself. Could we be approaching a similar revolution? Could Einstein's general relativity be an approximation that works wonderfully in most situations, but requires replacement when dealing with the cosmos as a whole? Maybe on truly vast scales, space and time behave differently than our current equations suggest. Maybe there are extra dimensions that become relevant at cosmic distances. Maybe quantum effects that are negligible locally become significant when integrated across the observable universe. But here's the problem with modifying gravity. When you change Einstein's equations to eliminate the need for dark energy, you typically create new problems elsewhere. The modifications that work for explaining cosmic acceleration often predict things we don't observe, or fail to explain things we do observe, or require fine-tuning that's even more implausible than dark energy itself. It's like fixing a leak in a dam by plugging it with your finger. You've solved one problem, but created several others, and you're still stuck with your finger in a hole you can't remove it from. So we're left with dark energy, this bizarre entity that seems to violate everything we think we understand about physics, that requires us to accept that most of the universe is made of something we cannot see or touch or understand, that the vacuum of space is alive with invisible energy whose origin and nature remain completely mysterious. We've built an elaborate theoretical structure around it, given it a place in our cosmological models, predicted the fate of the cosmos based on it. But have we really explained anything? Or have we just given a sophisticated name to our confusion? Think about what we're claiming. We're saying that empty space, pure nothingness, the void between stars and galaxies, has energy. Not metaphorical energy, but real, physical energy that can do work, that can push galaxies apart, that can determine whether the universe will expand forever or eventually collapse. We're saying that this energy has remained perfectly constant for billions of years, maintaining exactly the same density in every cubic centimeter of space throughout all of cosmic history. We're saying that it's the dominant component of the universe, more abundant than stars, more influential than dark matter, the single most important factor in cosmic evolution. And we're basing all of this on observations of distant supernovae that appear dimmer than expected, on measurements of the cosmic microwave background that show specific patterns of temperature fluctuations, on large-scale structure surveys that reveal how galaxies are distributed through space. These are indirect inferences, chains of reasoning built on assumptions about how light travels, how matter clusters, how the early universe evolved. Each link in the chain is reasonable, defensible, supported by physics we think we understand. But chains can break, assumptions can be wrong, and the longer the chain of inference, the more opportunities for error to creep in. This isn't to say the evidence is weak. It's not. The evidence for cosmic acceleration is strong and comes from multiple independent sources. But strong evidence for acceleration isn't the same as strong evidence for dark energy, because acceleration could have other explanations. It could be a signature of modified gravity, or an effect of living in an unusual cosmic environment, or a consequence of poorly understood astrophysical processes that dim distant light, or something we haven't even thought of yet. The universe is under no obligation to make sense to us. It doesn't care about our theories, our equations, our need for tidy explanations. It simply is what it is, operating according to laws we're struggling to decipher with limited information and finite minds. And sometimes, perhaps more often than we'd like to admit, the universe surprises us, reveals that our confident proclamations were premature, that our beautiful theories were elegant mistakes. Dark energy might be real. It might be exactly what our current models suggest: a cosmological constant, vacuum energy, the intrinsic tension of space itself, driving eternal acceleration toward a cold, dark, empty future. But it might also be something we look back on with embarrassment, a historical footnote in the story of cosmology. An example of how even rigorous science can lead us astray when the evidence is ambiguous and the theoretical frameworks are incomplete. The stage is set. The mystery is established. We have observations that seem to demand explanation, and we have an explanation that seems to demand belief despite being fundamentally inexplicable. We're balanced on the edge between knowledge and ignorance, between confidence and doubt, between acceptance and skepticism. And the question that should gnaw at you, the question that should keep you awake at night staring at the ceiling, is this: are we discovering the universe, or are we inventing it? Are we reading the cosmic text correctly, or are we seeing patterns in noise, constructing elaborate interpretations of data that might mean something completely different from what we think? The universe is accelerating away from itself. This is what we observe. But perhaps observation without understanding is just another form of deception. A deception so subtle, so insidious, that we mistake our own confusion for clarity, our assumptions for facts, our models for reality. And if dark energy is a deception, then it's the ultimate cosmic deception, woven into the very fabric of space itself, hidden in plain sight, across billions of light years, mocking our attempts to comprehend it, even as we claim to have measured it to exquisite precision. Let's descend deeper into the rabbit hole. Let's examine the theories that attempt to explain dark energy, and in examining them, discover that each explanation opens more questions than it answers. Each solution reveals new abysses of uncertainty. Because the true mystery of dark energy isn't just that we don't understand it. It's that every attempt to understand it reveals how little we understand about reality itself. Start with the simplest explanation, the one Einstein himself proposed and then abandoned: the cosmological constant. Imagine that space itself has an inherent energy density, a fundamental property baked into the structure of reality. Empty space isn't truly empty. It's fizzing with quantum activity, a seething ocean of virtual particles that pop into existence and vanish in intervals so brief that they exist in a liminal state between being and not being. These quantum fluctuations create an energy density that remains constant no matter how much space expands. Create more space, and you automatically create more of this vacuum energy, as if emptiness itself is a substance that can be manufactured infinitely without cost. This is simultaneously the most straightforward and the most bewildering explanation for dark energy. Straightforward because it requires adding just a single number to Einstein's equations, the cosmological constant, represented by the Greek letter lambda. That's it. One constant unchanging throughout all of space and time, and suddenly your equations predict cosmic acceleration. The mathematics is elegant, almost suspiciously simple. Too simple, perhaps, because here's where the bewilderment begins. When you actually try to calculate what this constant should be using quantum field theory, you get an answer that makes the observed value look like a rounding error. The vacuum should be boiling with energy, so much energy that it would tear the universe apart, preventing galaxies from forming, stars from igniting, atoms from holding together. The fact that we exist at all means that somehow, impossibly, almost all of this vacuum energy has been cancelled out, leaving behind only a tiny residue, 1 part in 10 to the power of 120 of what should be there. Imagine you're trying to balance a pencil on its tip. Now imagine that pencil is balanced not on a table, but on the head of another pencil, which is balanced on another pencil. And this tower of balanced pencils extends for 120 stories. The slightest tremor, the faintest breath of air, and the whole structure collapses. That's the level of fine-tuning required to explain why the cosmological constant has the value it does. It's not impossible. The pencils are balanced, after all, because we exist to observe them. But it strains credulity to the breaking point. So perhaps the cosmological constant isn't constant at all. Perhaps dark energy is dynamic, evolving, changing over time in ways too subtle to detect with current observations, but significant over cosmic epochs. Physicists call this hypothetical dynamic energy quintessence, and it's worth understanding what this means because it transforms dark energy from a simple number into a field, something that fills space like an invisible ocean with currents and tides and depths that vary from place to place and moment to moment. Think of quintessence as a field permeating all of reality, similar to the electromagnetic field but operating on cosmic scales. Just as the electromagnetic field can store energy in the electric field between charged particles, in the magnetic field around a current-carrying wire, The quintessence field stores energy throughout space. But unlike the electromagnetic field, which can have zero energy when no charges or currents are present, the quintessence field never quite reaches zero. It maintains a baseline energy density that drives cosmic acceleration. But this density can change, slowly rolling down a potential energy landscape like a ball descending a gentle slope. Imagine reality as a vast landscape, and the quintessence field is a ball sitting somewhere on this landscape. Where the ball sits determines the energy density of space. If the landscape is perfectly flat where the ball rests, you get a cosmological constant. The ball doesn't roll, the energy doesn't change, everything remains static. But if the landscape has even the slightest slope, the ball will roll, albeit perhaps incredibly slowly, and the energy density will evolve over time. The acceleration of the universe might be increasing or decreasing, and the ultimate fate of the cosmos depends on where the ball is rolling and what lies at the bottom of the slope, or if there even is a bottom. This sounds more satisfying than a cosmological constant, doesn't it? A field that evolves feels more natural, more physical, less like an arbitrary number inserted into equations to make them work. And quintessence has another appealing feature. It can potentially explain why dark energy has approximately the same energy density as matter today. If quintessence is slowly evolving, perhaps it only recently became dominant, and we happen to be living in the cosmic epoch when dark energy and matter have comparable densities, not because of miraculous fine-tuning, but because the field naturally passes through this phase. But, and this is a devastating but, quintessence doesn't actually solve the cosmological constant problem. It just relocates it. Instead of asking why the cosmological constant has the tiny value it does, we're now asking why the quintessence field has the properties it does. Why does it have exactly the right potential energy landscape to drive the observed acceleration? Why does it interact so weakly with matter that we haven't detected it despite its cosmic dominance? Why did it become important now, in the brief cosmic moment when intelligent life happens to be observing the universe? Every answer spawns new questions. It's like trying to understand a reflection without realizing you're looking in a mirror. You can describe what you see in exquisite detail, map every feature, note every color and contour, but you're describing the image, not the thing itself. Quintessence might be a better description of dark energy's behavior, but does it actually explain what dark energy is? Or are we just adding complexity to our models without gaining genuine understanding? Then there's the radical alternative. Abandon dark energy entirely and modify gravity itself. This is where cosmology becomes truly heretical, where we question not just our understanding of dark energy, but the foundational theory that has guided physics for over a century. General relativity is one of the most beautiful, most successful, most thoroughly tested theories in all of science. But what if it's wrong? Not wrong in the sense of being completely false, but wrong in the way Newton's gravity was wrong. Accurate enough for most purposes, but breaking down under extreme conditions, requiring replacement with a deeper, more comprehensive theory. Modified gravity theories come in many flavors, but they share a common theme. On cosmological scales, gravity doesn't behave the way Einstein's equations predict. Perhaps there are additional terms in the gravitational field equations that only become significant across billions of light years. Perhaps gravity is slightly weaker on cosmic scales than on solar system scales, creating an apparent acceleration without requiring dark energy. Perhaps space and time have properties that only manifest when you're dealing with the observable universe as a whole. Extra dimensions that curl up on small scales but stretch out on large ones, or quantum corrections to classical gravity that accumulate over cosmic distances. One of the most intriguing proposals is called FED-R gravity, where instead of space-time curvature being directly proportional to matter and energy density, it's related through a more complicated mathematical function. Imagine reality as a film reel, but instead of running at constant speed, the film can stretch and compress, with some frames lasting longer than others, and some regions of the frame distorting differently than others. In standard general relativity, the relationship between curvature and content is linear, straightforward. In FR gravity, it's non-linear, allowing for rich new behaviors that could mimic dark energy's effects without actually requiring a mysterious energy component. But modified gravity faces brutal challenges. When you change Einstein's equations to eliminate dark energy, you typically break something else. The modifications that work for cosmic acceleration often predict wrong answers for other observations. The motion of galaxies within clusters, the growth rate of cosmic structure, the behavior of gravitational waves. It's as if the universe has been carefully designed to resist our attempts at simple explanations, to force us into accepting either dark energy or even more Baroque modifications to fundamental physics. And there's a deeper issue, one that cuts to the heart of how we do science. We're trying to modify a theory that works extraordinarily well in every other context, based on observations at the extreme edge of what we can measure. We're essentially saying general relativity is perfect for describing black holes, gravitational waves, GPS satellites, the orbit of Mercury, binary pulsars, but breaks down when describing the expansion of the universe itself. That's possible, certainly, but it requires us to believe that Einstein's theory has an exquisitely narrow domain of validity, that it works everywhere except in the one place where we need it most. Perhaps the problem isn't with gravity or with dark energy specifically, but with our assumptions about the universe's geometry and contents. What if we're not living in a typical region of the cosmos? What if our local neighborhood, everything within a few billion light-years, is unusually empty compared to the cosmic average, a giant void in the distribution of matter? If we're near the center of such a void, light from distant galaxies would travel through regions of varying density on its journey to us, and this could create an apparent acceleration even in a universe that's not actually accelerating. This is the void hypothesis, and it's deeply troubling because it challenges one of cosmology's fundamental assumptions, the cosmological principle, the idea that the universe looks roughly the same everywhere when viewed on large enough scales. We assume that our patch of the universe is typical, representative, not special. But what if that's wrong? What if we're observing from an unusual vantage point, and the dark energy we think dominates the cosmos is actually a local peculiarity, a trick of perspective caused by our accidental location in a vast underdensity? The void hypothesis is controversial and faces significant observational challenges. We should see specific signatures in the cosmic microwave background if we're in a giant void, and those signatures aren't there, or at least not obviously. But the fact that we even have to consider such possibilities reveals how uncertain our cosmic understanding really is. We're building grand theories on observations that could be distorted by local conditions, inferring universal laws from data that might only describe our cosmic neighborhood. Now let's confront the paradoxes, the truly unsolvable puzzles that lurk at the heart of dark energy, like philosophical landmines waiting to detonate our certainty. Because even if dark energy is real, even if it's exactly what our best models suggest, its existence raises questions so profound that they threaten to unravel our entire framework for understanding reality. The first paradox is the fine-tuning problem, but understood in its full, existentially disturbing depth. The amount of dark energy in the universe appears to be calibrated with impossible precision. Too much, and space would have expanded so rapidly that matter could never clump together. No galaxies, no stars, no planets, no life. Too little, and the universe would have recollapsed long before now, crushed back into a singularity before the first stars could form. The observed value sits in an extraordinarily narrow window that permits the existence of complex structures like galaxies and, ultimately, consciousness. Change dark energy by even 1 part in 10 to the power of 120, and the universe becomes sterile. This is fine-tuning so extreme that it makes the mind rebel. It's as if the universe was designed specifically to allow for observers like us, as if the constants of nature were dialed in with exquisite care to make existence possible. But physics doesn't do design. Physics doesn't have intentions or purposes. Physics just is. So how do we explain this apparent cosmic conspiracy? One answer is the anthropic principle. And it's worth sitting with this idea because it's both intellectually satisfying and deeply unsettling. The anthropic principle says, we observe these particular values for physical constants because only in a universe with these values could observers exist to make observations. It's a selection effect. We're not finding the universe fine-tuned for life. We're finding that in any universe that produces intelligent observers, those observers will measure constants compatible with their own existence. It's inevitable, tautological even. We couldn't observe a universe where dark energy was too large because we wouldn't exist to observe anything. But this explanation only works if there are many universes. A vast multiverse where every possible value of dark energy is realized somewhere. In most of these universes, dark energy is too large or too small, and they remain empty, devoid of complexity or consciousness. But in a tiny fraction, perhaps an infinitesimally tiny fraction, the value happens to fall in the narrow range that permits structure formation. And these rare universes produce observers who wonder why their universe seems so special. The multiverse is a wild idea, one that pushes the boundaries of what we can meaningfully call science. If other universes exist but are forever beyond our reach, causally disconnected by the structure of space-time itself, can we really claim they're scientific entities? Or are we engaging in metaphysics, constructing elaborate, unfalsifiable stories to explain observations we don't understand? The multiverse might be real. Some versions of inflation theory naturally produce pocket universes with different physical properties. But it might also be a just-so story, a myth we tell ourselves to avoid confronting the mystery of fine-tuning. And even if the multiverse exists, it doesn't explain why the probability distribution across universes is such that observers are possible at all. Why should the ensemble of possible universes include any with parameters suitable for life? You've just pushed the fine-tuning problem up one level, from our universe to the multiverse itself. It's turtles all the way down. And at some point, You have to stop asking why and accept that some things simply are. There's another paradox, more subtle but equally disturbing. The coincidence problem. Why is dark energy becoming dominant now in this cosmic epoch, precisely when intelligent life happens to be observing the universe? For most of cosmic history, matter dominated and dark energy was negligible. In the far future, dark energy will completely dominate and matter will be diluted to near irrelevance. But right now, in this brief window lasting perhaps a few billion years, matter and dark energy have comparable densities. We're living through a special time, a cosmic transition, and that seems suspicious. It's like opening a history book to a random page and landing exactly on the page describing the fall of the Roman Empire, or the signing of the Declaration of Independence, or the first moon landing. The odds of randomly hitting such a significant moment seem vanishingly small. Yet here we are, observing the universe at the precise epoch when dark energy is overtaking matter as the dominant component. Either this is an extraordinary coincidence, or there's a reason why observers necessarily arise during this transition period, or our observations are somehow systematically biased in ways we don't understand. Some physicists suggest that complex structures, galaxies, stars, planets, life, can only form during this transition period. Before dark energy became important, the universe was too young and dense. After dark energy completely dominates, structure formation will essentially cease, and the universe will become a cold, empty expanse where nothing interesting happens. Perhaps consciousness can only emerge in universes during their middle age, when conditions are neither too violent nor too quiescent. If that's true, then every observer in every universe will necessarily find themselves living through a similar transition. And there's no coincidence at all. But this feels like motivated reasoning, doesn't it? It's an explanation custom-tailored to make our observations seem inevitable rather than unlikely. We're taking the fact that we exist now and concluding that we had to exist now, which is circular logic dressed up in cosmological clothing. Maybe the coincidence is just that, a coincidence. The universe doesn't care about our intuitions regarding probability. It simply unfolded in the way it did, and we happen to be here to observe this particular epoch. Demanding an explanation for every apparent coincidence might be asking too much of reality. Then there's the measurement problem. And I don't mean the quantum mechanical measurement problem, though the two are eerily related. I mean the practical difficulty of actually measuring dark energy's properties with enough precision to distinguish between different models. Dark energy only reveals itself through its effects on the universe's expansion rate over cosmic time. But measuring that expansion rate requires observing objects billions of light years away, which means looking billions of years into the past. And all the light from those objects has been traveling through a universe we don't fully understand, potentially being affected by processes we haven't accounted for. Every measurement we make is filtered through layers of uncertainty. We have to understand how supernovae work, how their light travels through intergalactic space, how cosmic expansion affects wavelengths, how our telescopes detect and interpret photons that have been journeying across the void since before Earth existed. Each layer introduces potential systematic errors, biases that could mimic dark energy's signature or hide its true properties. And because we can't directly observe dark energy, can't capture it, study it in isolation, manipulate it in experiments, we're always working with indirect inferences, chains of reasoning that are only as strong as their weakest link. What if there's a systematic error we haven't identified? What if distant supernovae are intrinsically different from nearby ones in subtle ways that our models don't capture? What if intergalactic dust has properties we don't understand? Dimming light in frequency-dependent ways that mimic distance? What if the expansion of space doesn't work exactly the way Einstein's equations predict? Not because gravity is modified, but because space itself has properties we haven't imagined. Any of these possibilities could make dark energy appear to exist when it doesn't, or could make its properties appear different from what they really are. This is the nightmare scenario for cosmology, that we've built an elaborate theoretical edifice on a foundation of systematic errors. That dark energy is a mirage created by our imperfect understanding of astrophysics and our limited ability to probe the distant universe. It's unlikely. The evidence for cosmic acceleration comes from multiple independent methods, and they all point in the same direction. But unlikely doesn't mean impossible. Science has been wrong before, spectacularly wrong, even when the evidence seemed overwhelming and came from multiple sources. And lurking beneath all these paradoxes is a deeper question, one that philosophers and physicists have wrestled with for centuries. What does it mean to explain something? When we invoke dark energy to account for cosmic acceleration, have we explained anything? Or have we simply labeled our ignorance, given a technical name to a phenomenon we don't understand? True explanation requires mechanism, causation, a narrative that connects cause to effect through principles we can grasp. But dark energy doesn't give us that. It's a placeholder, a variable in equations, a thing we've defined into existence to make our models work. Maybe that's all explanations ever are. Stories we tell, narratives we construct, patterns we impose on observations. Maybe the universe doesn't operate according to explanations at all, doesn't follow principles or laws in any meaningful sense. Maybe it just is, and our desperate search for understanding is a cognitive artifact, a feature of brains evolved to find patterns and causes in a reality that contains neither. Maybe dark energy is real, and maybe it's the ultimate cosmic deception. Not because it's hiding something, but because in trying to explain it, we're deceiving ourselves about what explanation means. We stand at the precipice, staring into an abyss of uncertainty. Every theory we construct reveals new mysteries. Every paradox we examine opens deeper questions. Every measurement we make could be subtly wrong in ways we can't detect. Dark energy might be vacuum energy, or quintessence, or modified gravity, or a measurement error, or something we haven't even conceived. And the most disturbing possibility of all? It might be all of these and none of these. Something so alien to our categories of thought that all our attempts to understand it are fundamentally misguided, like ancient astronomers trying to understand planetary motion without realizing that Earth itself is a planet. The heart of the mystery beats with uncertainty. And that rhythm, that constant pulse of doubt and wonder, might be the only truth we can ever grasp about dark energy. Stop for a moment. Put down whatever you're doing. Feel your heartbeat. Notice your breath moving in and out, automatic and constant. You are here now, reading these words, thinking these thoughts. You are real. Your consciousness is real. Your memories are real. Everything you've experienced, everyone you've loved, every moment of joy and pain and mundane tedium, all of it happened. All of it matters, doesn't it? But here's what the dark energy mystery forces you to confront. If 70% of reality is something we cannot understand, cannot detect, cannot explain, if the dominant force shaping the universe is fundamentally mysterious to us, then how much of what you think you know about existence is actually true? You exist in a reality where the vast majority of what's real is completely invisible to you, where the fate of everything you care about is being determined by forces you cannot perceive, where the very fabric of space might be a cosmic illusion you're mistaking for truth. Think about what this means. Right now, as you exist in this moment, dark energy is pulling the universe apart. Not metaphorically, not in some abstract mathematical sense. Actually, physically pulling. Every second, space is expanding, and that expansion is accelerating, driven by this mysterious energy that fills every cubic centimeter of the cosmos. The galaxy you see when you look up at the night sky, Andromeda, our nearest large neighbor, is currently rushing toward us, defying the cosmic expansion because local gravity is strong enough to overcome it. In about 4 billion years, it will collide with the Milky Way in a slow-motion catastrophe that will reshape both galaxies into something new. But after that? After the collision? After the merger? After our descendant galaxy settles into its new configuration? Dark energy will win. It will push every other galaxy away from us with ever-increasing speed until they vanish beyond the OEP cosmic horizon, their light red-shifted into invisibility, their very existence erased from our observable universe. Future beings, if any exist, will look up at the night sky and see almost nothing. No distant galaxies, no cosmic microwave background filled with information about the universe's history. Just a handful of nearby stars, and beyond them, an ocean of darkness that extends forever in all directions. They will be cosmologically isolated, trapped in a pocket of space surrounded by nothingness, and they will have no way to discover that there was once a larger universe, no way to learn about the Big Bang or cosmic expansion or dark energy. They won't be able to do cosmology because cosmology will be impossible from their vantage point. All the evidence will have literally fled beyond their reach, carried away by the expansion of space itself. They will be imprisoned in ignorance, not because they're not intelligent enough, but because the universe will have hidden its own history from them. And here's the existential dagger. We might already be those future beings. We might be living trillions of years after the universe began, in an epoch where most of the evidence about reality's true nature has already disappeared beyond the cosmic horizon. What we think is the observable universe, 93 billion light-years across, filled with hundreds of billions of galaxies, might be a tiny, atypical remnant of something far vaster and stranger that we can no longer see. Dark energy might not be mysterious because it's fundamentally inexplicable. It might be mysterious because we're observing the universe during an era when the clues needed to understand it have already vanished into the void. You cannot know. You cannot ever know. You are trapped in your cosmic moment, able to observe only what light has had time to reach you, able to measure only what happens within your causal horizon. The universe beyond that boundary is forever. Inaccessible. Not practically inaccessible, like distant planets we might visit someday with better technology, but fundamentally inaccessible, walled off by the structure of space-time itself. No signal from those distant regions will ever reach you. No information will ever cross the divide. They might as well not exist, except they do exist, presumably. And their existence affects the universe in ways you're completely blind to. This is the cosmic horror that dark energy reveals. Not the horror of monsters or violence, but the horror of epistemic limits, of knowing that reality extends far beyond what you can comprehend, that your understanding is fundamentally and permanently incomplete. You are an intelligent consciousness trapped in a bubble of ignorance, desperate to understand a universe that actively hides itself from you, that expands faster than light can traverse it, that buries its secrets beneath layers of distance and time and mysterious energies you cannot fathom. And it's accelerating. That's the truly nightmarish part. If the expansion were constant, you could at least maintain equilibrium. The cosmic horizon would stay at a fixed distance, and while you couldn't see beyond it, at least it wouldn't be shrinking. But acceleration means the horizon is moving away from you, and galaxies that are currently visible will eventually disappear, and the observable universe is actually getting smaller in terms of what you can access. With each passing moment, information is being destroyed, not by entropy or decay, but by the expansion of space itself, which stretches light into longer and longer wavelengths until it becomes undetectable, carrying away knowledge that will never return. You are living through the universe's slow-motion suicide, watching it tear itself apart at an ever-increasing pace, and there is absolutely nothing you can do about it. Dark energy is inevitable, unstoppable, indifferent to life or consciousness or meaning. It doesn't care that you exist. It doesn't care about your civilizations, your art, your love, your desperate search for understanding. It simply pushes relentlessly, expanding space and erasing futures until eventually, perhaps a Google years. From now, a 1 followed by 100 zeros, a timescale so vast that the current age of the universe is less than a single quantum fluctuation. Even black holes will evaporate, even protons might decay, and the universe will become a thin soup of radiation and particles so spread out that they might go trillions of years without encountering each other. That's the future dark energy is creating. The big freeze, heat death, maximum entropy, a cosmos where nothing interesting can ever happen again because there's no free energy left to drive processes, no gradients to create order, no possibility for complexity or life or thought. Every atom that exists will still exist, presumably, but they'll be scattered so far apart, moving away from each other so quickly, that the universe might as well be empty. It will be a graveyard of matter, a tomb of frozen potentiality, expanding forever into absolute zero and absolute darkness. unless dark energy changes, unless it decays or evolves or reverses, unless the quintessence field, if that's what it is, begins rolling back up its potential energy landscape instead of down. Unless modified gravity theories are correct, and the acceleration will eventually slow. Unless the universe is cyclic, and what appears to be endless expansion is actually the first half of an oscillation that will eventually reverse into contraction. Unless we're wrong about everything, but you don't know. You can't know. You're riding this cosmic wave with no control, no certainty, no guarantee that the future will be anything other than increasing isolation and eventual extinction of all possible complexity. Your existence, humanity's existence, Earth's existence, the Sun's existence, is a brief flicker of structure in the universe's long march toward homogeneity. You are temporary, not just in the sense that you'll die someday, but in the sense that everything you are, everything you're part of, everything that gives your life context and meaning will eventually be erased so completely that no trace will remain. Dark energy ensures this. It is the universe's ultimate cleaning mechanism, sweeping away structure, erasing information, guaranteeing that nothing lasts. And yet you exist anyway. Despite the cosmic odds, despite the apparent meaninglessness that dark energy seems to promise, despite living in a universe where most of reality is invisible, where the future is bleak, where understanding seems forever beyond reach, you still experience joy, you still love, you still find meaning in transient moments, you still look up at the night sky and feel wonder rather than terror. Maybe that's what makes you human, or conscious, or alive, whatever category best captures what you are. You exist in defiance of cosmic indifference. You create meaning in a universe that provides none. You care about things that the fundamental forces of nature don't care about. You are a way for the cosmos to know itself, in Carl Sagan's beautiful phrase, even if that knowing is partial, temporary, and ultimately doomed. But what if that's the point? What if consciousness exists precisely because the universe is accelerating? Because dark energy creates conditions where observers necessarily arise during a brief window of cosmic history? What if you're not an accident, but an inevitability, not a random fluctuation, but a necessary feature of how reality works? Some versions of the anthropic principle suggest this. They argue that observers can only exist in universes fine-tuned for complexity, and by existing, you're proving that your universe must be fine-tuned. Your consciousness is evidence that the constants of nature couldn't be otherwise. Not because of design or purpose, but because you wouldn't be here to observe a universe with different constants. This is simultaneously comforting and terrifying. Comforting because it means your existence isn't random or meaningless. You're a necessary consequence of physical law, as inevitable as gravity or entropy. Terrifying because it means you're trapped in a tautology, proving only that you exist in a universe where you can exist, learning nothing deeper about why reality has the properties it does, or why anything exists at all. What if the universe is alive, and you are just its fleeting thoughts? Not literally alive in the biological sense, but alive in the sense of being a self-organizing system that generates complexity and consciousness and perhaps even purpose through purely physical processes. Dark energy would then be the universe's metabolism, the force that drives its evolution from simple to complex and eventually back to simple again. A cosmic cycle of thought and forgetting played out over timescales that make geological epochs seem instantaneous. In this view, you're not separate from the universe. You are the universe, a localized region where it has become aware of itself, where matter has arranged itself into patterns capable of reflecting on their own existence. Your thoughts are the universe's thoughts. Your questions are the universe's questions. When you wonder about dark energy, the cosmos is literally wondering about itself, examining its own nature through the temporary lens of your consciousness. But if that's true, then what happens when you die? When your brain stops functioning and your consciousness winks out, does that fragment of cosmic self-awareness simply vanish? Or does it return to some larger pool of potentiality, waiting to emerge again in some other configuration, some other time, some other place? Is death the end, or is it a transformation, a redistribution of the pattern that constitutes you back into the quantum foam from which it emerged? You cannot answer these questions with science. You can barely frame them coherently. You're asking about the relationship between matter and consciousness, between physics and experience, between the objective world and subjective awareness. These are the deepest mysteries in philosophy, and dark energy doesn't help solve them. It makes them worse, because it reminds you that even the objective physical world is fundamentally mysterious, that matter itself is mostly composed of things you don't understand. If time is an illusion, then everything you've ever done might have already happened infinite times before. Einstein's relativity suggests that past, present, and future all exist simultaneously. That time is just another dimension we move through. That the flow of time we experience is a trick of consciousness rather than a feature of reality. The block universe, physicists call it. A four-dimensional structure where every moment exists eternally, where your birth and death and every instant in between are permanent features of space-time, frozen in place like words on a page. If this is true, then you never really change. The you reading this sentence exists forever at this moment, and the you who existed yesterday exists forever at that moment. And they're not the same you. They're different slices of a four-dimensional object threading through time. You are not a thing that persists. You are a process that extends. And dark energy's acceleration doesn't change any of this. The future where galaxies have disappeared beyond the horizon exists just as surely as the past, where the universe was hot and dense. Time doesn't flow toward it. It simply is, waiting in the eternal now that relativity describes. This should be liberating. If every moment exists permanently, then nothing is truly lost. Every joy you've experienced is still happening, somewhere in the block universe. Every person you've loved still exists at the moments you shared with them. Death isn't an ending, but a boundary. The edge of your four-dimensional world line, as real and permanent as your birth. But it's not liberating, is it? It's paralyzing. It means you have no free will, no ability to change anything, because every choice you'll ever make is already laid out in the structure of space-time. It means the future is fixed, predetermined, knowable in principle, even if you lack the information to predict it. It means dark energy's victory is already complete. The heat death already exists in the far future of the block universe, and you're just moving through time toward it like a train following predestined tracks. Unless the block universe is wrong. Unless time is more than relativity suggests. Unless consciousness itself plays a role in collapsing quantum superpositions, choosing which branch of reality becomes actual, creating the flow of time through the act of observation. This is controversial, rejected by most physicists, but it persists because it addresses something that purely mechanical descriptions of reality leave out: the undeniable fact of your experience, the reality of now, the sensation of becoming that seems fundamental to consciousness. You feel time passing. You experience change. You remember the past and anticipate the future in ways that don't feel like illusions. Maybe that's because they're not illusions. Maybe consciousness does something real, creates something that physics alone cannot account for. And maybe dark energy is connected to this in ways we don't understand, a bridge between the physical and the experiential, between what is measured and what is felt. Or maybe you're grasping at straws, desperate to find meaning in a universe that offers none, inventing connections between consciousness and cosmology, because you can't bear the alternative, that you are nothing but atoms obeying laws, temporary patterns in a universe that doesn't care whether you exist or not, spinning stories about purpose and meaning in a reality that contains neither. The weight of what you've learned settles on you like gravity. Dark energy is not just a scientific mystery. It's an existential crisis. It's proof that you live in a universe fundamentally beyond your comprehension, where the very fabric of space is mysterious, where the future is bleak, where isolation is inevitable, where ignorance is guaranteed by the structure of reality itself. You are cosmically alone, epistemically trapped, ontologically confused, and temporally doomed. And yet here you are, still reading, still wondering, still hoping, perhaps, that understanding is possible, that meaning can be found, that existence is worth the cosmic terror it entails. That might be the most remarkable thing about consciousness. Not that it exists despite the horror, but that it persists in finding beauty, meaning, purpose, even when confronted with the abyss. You stare into the darkness, and instead of despair, you feel awe. You learn about dark energy's promise of heat death, and instead of giving up, you keep asking questions. Maybe that's what it means to be human in a universe dominated by dark energy, to be small and temporary and ignorant, yet defiant, to seek understanding even when understanding seems impossible, to create meaning even when meaning seems absent, to love and build and dream even when the cosmos itself is accelerating toward your obliteration. The stakes couldn't be higher. The mystery couldn't be deeper. And you, fragile, temporary, confused, you're the universe's best attempt at understanding itself before dark energy tears everything apart. So, here it is, the revelation that ties everything together, that recontextualizes every mystery you've encountered, that transforms dark energy from a cosmological puzzle into something far more disturbing. Are you ready? Because once you see this, you cannot unsee it. Once you understand the implication, the universe will never look the same. What if dark energy isn't pushing the universe apart? What if we're falling? Think about it. Imagine you're in an elevator with no windows, plummeting down a shaft. You feel weightless. Objects around you float. To you, it appears that gravity has been turned off, that some mysterious force is making everything drift apart. But you're not in zero gravity. You're in free fall. The sensation of weightlessness is an illusion created by your frame of reference. You and everything around you are accelerating together. And from inside that accelerating frame, it looks like forces have disappeared when actually, you're being pulled by the strongest force of all. Now scale this up. Imagine the observable universe, all 93 billion light-years of it, every galaxy, every star, every atom, is falling into something. Not falling through space, but falling through time, accelerating toward some cosmic attractor so massive, so distant, so far beyond our observational horizon that we can't see it. From our perspective, inside this cosmic freefall, it looks like space is expanding and accelerating. We measure dark energy pushing everything apart. But what if we're measuring the symptoms of falling, not pushing? What if the acceleration we observe is the signature of the universe plunging toward something we cannot perceive? What could we be falling toward? Perhaps a region of space-time with different properties. A domain where physical laws transition into something alien. Perhaps the universe is not alone. Perhaps we're embedded in a higher dimensional space, and our four-dimensional bubble is falling through that larger reality like a raindrop descending through air. Perhaps time itself has geometry, and we're sliding down a temporal gradient toward some cosmic singularity hidden in the future. Perhaps the Big Bang wasn't the beginning, but the rebound from a previous collapse. And we're already falling back toward the next compression. The next cosmic reset, or perhaps, and this is where the horror deepens, perhaps we're falling into a black hole. Not a stellar mass black hole, not even a supermassive black hole at a galaxy's center, but something cosmological, something so vast that its event horizon encompasses our entire observable universe. You know how objects falling into a black hole experience time dilation, watching the outside universe speed up while their own clocks run normally? What if we're already past the event horizon? What if the cosmic acceleration we observe is actually time itself running at different rates in different regions, creating the illusion of spatial expansion when really we're experiencing the time geometry of an event horizon? This would mean we're trapped, not just cosmologically isolated by distance, but fundamentally imprisoned inside a region of space-time from which escape is impossible, where every future trajectory leads inward toward the singularity hidden somewhere in what we call the far future. The universe wouldn't be expanding toward heat death. It would be contracting toward catastrophic compression. And we're simply too deep inside the event horizon to perceive the true geometry of our cosmic prison. Picture it. Every galaxy rushing away from every other galaxy. Space itself stretching at accelerating rates, but it's all an illusion of perspective. In reality, everything is falling inward, collapsing, converging on a point hidden beyond the veil of our observational limits. The cosmic microwave background, that ancient light we use to study the early universe, it might be light from outside the event horizon, the last photons that managed to fall in with us, carrying information about a larger cosmos we're now cut off from. Dark energy isn't a mysterious force pervading space. It's the signature of our gravitational imprisonment, the evidence that we're on the wrong side of a cosmic boundary. And here's the truly devastating implication. If we're inside an event horizon, then the future doesn't exist yet. Not in the block universe sense, where all of time is laid out eternally. Inside a black hole, space-time is so warped that the singularity isn't located in space. It's located in time. It's not somewhere you could travel to. It's somewhere you inevitably reach. The singularity is in your future, unavoidable, inescapable, approaching not because you're moving toward it, but because time itself points in that direction. Every moment that passes brings you closer. not through motion, but through the simple fact of existing, of progressing from one instant to the next. What would this singularity be? Perhaps it's the moment when dark energy's density reaches infinity, when space has expanded so much that the fabric of reality tears apart in what cosmologists call the Big Rip. Perhaps it's a phase transition where the laws of physics change completely, where the quantum fields that define particles and forces shift to a lower energy state, rewriting the rules of existence. Perhaps it's the heat death itself, the moment of maximum entropy when time effectively stops because no further change is possible. Or perhaps it's something we can't imagine, something so alien to our understanding that we have no concepts to describe it. You would never know. From inside the event horizon, the singularity is hidden behind a veil of time. You can see your past, stretching back to the Big Bang. You can see your present, the universe around you accelerating apart. But you cannot see the singularity waiting in your future. It's coming, inevitable but cloaked in the structure of space-time itself. Dark energy would then be the universe's way of showing you that you're trapped, that escape is impossible, that every moment carries you one step closer to the end. Imagine the visual. A cosmos of galaxies, billions upon billions of them, each a swirling vortex of hundreds of billions of stars, all of them suspended in the darkness of space. From our perspective, they're rushing apart, fleeing each other at ever-increasing speeds, driven by the mysterious force we call dark energy. The expansion is accelerating. Space is stretching. The universe is growing. But now shift perspective. Rise above the observable universe. See it from outside, from a vantage point impossible yet necessary to understand the truth. And what you see isn't expansion at all. You see everything, every galaxy, every photon, every quantum of energy, falling together, converging, collapsing into a point that exists not in space, but in time. The apparent acceleration is just the increasing velocity of freefall. The cosmic horizon isn't receding. It's the edge of the event horizon, the boundary where light can no longer escape to infinity, where all trajectories curve inevitably inward. You are not watching the universe expand. You are watching it collapse, and you're collapsing with it, unable to perceive the truth because you're trapped inside the very geometry that's deceiving you. This is the ultimate cosmic deception. Not that dark energy is misunderstood or mismeasured, but that the entire framework we use to interpret observations might be inverted. We think we're watching expansion when we're experiencing contraction. We think we're headed toward cold isolation when we're headed toward hot convergence. We think we understand the universe's geometry when we're actually lost inside a black hole so large that its interior looks like an entire expanding cosmos. And you cannot prove this wrong. You cannot escape to check. You cannot observe from outside. All you have are measurements made from inside, interpreted through theories developed from inside, tested against observations made from inside. If you're in a cosmic black hole, every test you perform will confirm the illusion, because the illusion is your reality. Dark energy is real from your perspective, even if from some impossible external view, it's merely the signature of your imprisonment. Is this true? Probably not. Most cosmologists would reject this scenario, point out observational inconsistencies, argue that the equations don't support it. But you cannot know with certainty. You cannot be absolutely sure that your observable universe isn't the interior of something larger and more terrible. The very nature of event horizons means that those inside cannot see out, cannot confirm their location, cannot distinguish between being in an accelerating cosmos and being in a collapsing prison. So you're left with mystery, with multiple possible interpretations of the same observations, with the disturbing knowledge that reality might be fundamentally different from what every measurement suggests. Dark energy could be vacuum energy, quintessence, modified gravity, observational error, or it could be none of these. It could be the signature of something so profound that we don't even have the concepts to understand it properly. And here's the final twist. The thought that should haunt you as you look up at the night sky. If the universe is infinite, if the multiverse is real, if every possible configuration of matter and energy exists somewhere in the vast ensemble of possible worlds, then somewhere out there, in some bubble universe or quantum branch or distant cosmic domain, another version of you is experiencing this exact same revelation. They're reading these words, or thinking these thoughts, or staring at their sky and wondering if dark energy is real or if they're trapped in a cosmic black hole falling toward a singularity they cannot perceive. And they cannot know the truth any more than you can. They're just as trapped, just as uncertain, just as lost in the mystery. The universe has deceived them too. Or perhaps it has revealed a deeper truth than anyone expected. Perhaps dark energy is the cosmos's way of saying, reality is stranger than you imagined, more mysterious than you can comprehend, and you will never, ever reach the bottom of it. The galaxies spin. The expansion accelerates. The future approaches. And you are falling through time towards something you cannot see, calling it expansion, because that's all your trapped perspective allows you to perceive. Dark energy might be the ultimate deception, or it might be the ultimate truth. And from inside your cosmic prison, those two possibilities are indistinguishable. The mystery deepens. The abyss stares back, and the universe accelerates toward whatever waits beyond the horizon of your understanding. So where does this leave you? You've traveled through 13.8 billion years of cosmic history, examined the evidence for dark energy from every angle, confronted theories that challenge everything you thought you knew about space, time, and reality itself. You've stared into the mathematical abyss, where quantum mechanics predicts values wrong by 120 orders of magnitude. You've considered the possibility that the universe might be falling rather than expanding, that you might be trapped inside a cosmic event horizon, that everything you observe might be an elaborate deception woven into the fabric of space-time itself. And what have you learned? That dark energy might be real, that it might be illusion. That 70% of the universe is fundamentally mysterious, possibly unknowable, perhaps beyond the reach of science itself. That the cosmos is stranger, more complex, more deeply weird than anyone imagined before 1998 shattered our cosmological certainty. That every answer breeds new questions, every solution reveals deeper mysteries, every measurement might be subtly wrong in ways we cannot detect. But here's what else you've learned. That uncertainty is not failure. That mystery is not defeat. That living in a universe you don't fully understand doesn't diminish your existence. It elevates it. You are a conscious being in a cosmos dominated by something invisible, inexplicable, potentially deceptive. You are asking questions that might have no answers, seeking understanding that might be forever beyond reach. and you're doing it anyway. You're persisting in wonder despite the apparent futility. You're creating meaning in a universe that might be meaningless, finding purpose where physics provides none. That matters. That means something, not to the universe. The universe doesn't care, but to you, to us, to whatever pattern of consciousness has emerged from atoms and evolved to contemplate its own cosmic context. We are the universe's way of asking questions about itself, even when those questions might be unanswerable. Especially when those questions might be unanswerable. Dark energy will continue to accelerate the expansion, or we'll discover it was something else all along. Or we'll find that our entire cosmological framework needs replacing. Galaxies will continue their outward rush, carrying away information and possibilities and potential futures. The cosmic horizon will shrink or expand or remain stable, depending on which theory proves correct, if any theory proves correct. The universe will unfold according to laws we're still struggling to comprehend, heading toward a fate we can predict but not prevent, cannot change, perhaps cannot even properly understand. And throughout all of this, you'll still be here for your brief cosmic moment. At least, still wondering, still questioning, still searching for truth in a reality that seems designed to hide it from you. You'll look up at the night sky and see those distant points of light, knowing that most of them are galaxies, not stars, each containing billions of suns and perhaps trillions of planets. You'll know that space is expanding between them, that dark energy is driving them apart, that someday they'll vanish beyond the horizon of observation. You'll know all this, and you'll still find it beautiful, because beauty doesn't require permanence. Meaning doesn't require certainty. Wonder doesn't require complete understanding. You can appreciate the universe while acknowledging its mysteries. You can feel awe while confronting ignorance. You can love existence while accepting its temporary nature and inevitable end. So here's your call to action. Don't stop questioning. Don't accept easy answers. Don't let anyone, scientists, philosophers, this video included, convince you that the mystery is solved when it clearly isn't. Dark energy is a placeholder for ignorance. It might be real, it might be illusion, but either way, it represents the frontier of human understanding, the edge where knowledge meets mystery and theories meet their limits. Keep pushing against that frontier. Not just cosmologists and physicists, you, everyone who wonders about existence, who looks up at the night sky and asks why. Every question you pose, every doubt you express, every alternative you consider contributes to the collective human project of understanding reality. You might not solve the dark energy mystery, neither might anyone else, but the attempt matters. The search itself has value, even if it never reaches its destination. And consider this final, chilling possibility. What if dark energy is a message? What if the universe is trying to tell us something through this acceleration, this mysterious force, this cosmic deception? What if by studying dark energy, we're actually studying a clue left by reality itself? A breadcrumb trail leading toward some deeper truth about existence. What if the mystery is intentional, designed to provoke exactly this kind of questioning, this reaching beyond current understanding toward something more fundamental? Or what if it's the opposite? What if dark energy is reality's way of saying that some questions have no answers, that the universe doesn't operate according to principles we can grasp, that existence is fundamentally inexplicable? What if the cosmological constant problem, that catastrophically wrong prediction, is nature's way of telling us we're asking the wrong questions, using the wrong frameworks, thinking about reality in ways that are fundamentally misconceived. You cannot know. Perhaps you will never know. But you can keep asking. You can remain curious. You can refuse to accept that any mystery is truly unsolvable, even while acknowledging that this particular mystery might resist solution for centuries or millennia or forever. The universe expands. Dark energy accelerates. Galaxies flee into darkness. And you, impossibly, improbably, briefly, you exist. You are aware. You can contemplate these mysteries and find them meaningful. You are the universe looking at itself and asking, what am I? Why am I? How am I possible? Those questions echo across the cosmos. They will continue echoing long after you're gone, carried by future minds in future civilizations, on future worlds orbiting stars that haven't been born yet. The search for understanding is humanity's legacy, consciousness's gift to an unconscious universe. Dark energy might be the ultimate cosmic deception, or it might be the ultimate cosmic truth, or it might be both, or neither, or something so strange that both and neither are meaningless categories. But here's what's certain. The story isn't finished. The mystery remains unsolved. The universe keeps its secrets even as it reveals them, shows its cards even as it shuffles the deck. And somewhere out there, in the quantum foam, in the fabric of space-time, in the mathematical structure underlying reality, the answer waits, or doesn't wait, or exists in some state that transcends waiting and not waiting, that renders the question itself meaningless. Dark energy is the universe's greatest mystery, or its greatest deception, or its greatest revelation. And you beautiful, temporary, questioning pattern of atoms, you get to witness this cosmic drama unfold, even if you never see its conclusion. The universe may have no end. Time may stretch infinitely forward, carrying everything toward heat, death, and maximum entropy, and the ultimate silence where nothing can ever happen again. Or time may loop, or branch, or terminate in ways we cannot imagine. Reality may be stranger than we can suppose, as the biologist J.B.S. Haldane once said. It may be stranger than we can suppose, but maybe, just maybe, neither does your capacity to wonder end with your physical death. Maybe consciousness is more fundamental than matter. Maybe every questioning mind that has ever existed leaves some imprint on reality, some permanent mark in the structure of space-time, some quantum entanglement with the cosmos itself that persists beyond biological death. Maybe you are more than atoms temporarily arranged. Maybe you are the universe's way of knowing itself, and that knowing echoes eternally through dimensions we cannot perceive. Or maybe none of that is true. Maybe you're just atoms, briefly organized, soon to disperse back into the cosmic void. Maybe consciousness is an accident, meaning is a construct, purpose is a fiction. Maybe dark energy will win, and entropy will triumph, and everything interesting will cease, and the universe will expand forever into cold darkness, where nothing matters, because nothing can matter. But even if that's true, even if the bleakest cosmological predictions are accurate, you're here now, reading this, thinking this, wondering about dark energy and cosmic acceleration and the ultimate fate of reality. And that wondering, that questioning, that refusal to accept ignorance passively, that's what makes you human. That's what makes consciousness valuable. That's what makes existence meaningful, despite its apparent meaninglessness. The universe accelerates toward mystery, and so do you. The cosmos expands into darkness, and so does your understanding, reaching always toward horizons you may never cross, asking questions you may never answer, seeking truth in a reality that might be fundamentally deceptive. Keep searching, keep questioning, keep wondering. Because in a universe dominated by dark energy, by invisible forces, and mysterious accelerations and cosmic deceptions that hide reality even as they reveal it. In such a universe, the greatest act of defiance is to keep asking why. The story continues, the mystery deepens, and the universe, vast, ancient, accelerating, possibly deceiving you, waits to see what you'll discover next, or what will discover you.